I will discuss a little bit about, still proceed with single field inflation and give a few points about it, non-Gaussianity, and although this is somewhat outside of the mainstream of my lectures here, I will mention this idea, how is it comes out, the idea of eternal inflation, and then I will mostly spend time on alternative mechanisms to the inflaton mechanism of generating the adiabatic perturbations, which is curvaton mechanism. That's interesting because based on this mechanism, we will be able to figure out that there are possible sources of non-Gaussianity in this case, and also entropy modes. And if I have time, I will make a few comments on reheating. That's the idea. Originally, I thought I would talk also about the axions, but we're not ready yet for this discussion, so I will skip that. All right, anyway, so let's continue with single field inflation, and let's try to understand if there is a substantial non-Gaussianity there. And at the same time, we'll see that there are analogs of separation of scales that emerge in the inflation context as well. Okay, so that's kind of in line with what Riccardo Ratazzi was talking about, although from quite a bit different perspective. So let's try and calculate the first non-trivial correlation function, which is this: zeta of k1, zeta of k2, zeta of k3. Okay, this will be a non-Gaussian term because in the Gaussian random field, this 3-point correlation function vanishes, just zero. In principle, if you measure this correlation function, this is the whole function of invariance, and therefore you will be able to learn a lot about the perturbations generated and therefore about the mechanism of their generation. However, in the single field inflationary theory, you easily convince yourself that this is not zero, but very small. How can we do that? There is a nice idea by Maldacena, the same guy whom you know from completely different, ideas, that if you consider a particular limit when the k1 is much smaller than k2 and k3, then the physics is actually quite simple behind this. Oops. Never mind. The physics is quite simple because there is separation of scales. Physically, the mode with small momentum, it's a long wavelength mode, it really doesn't care about the short wavelength modes, which are around, little wiggles here and there. And it evolves just like we discussed yesterday. However, short and at some point it exits the horizon, and that happens early on in the history of the universe at inflation. Okay, so it exits the horizon early. However, the short wavelength modes now live in the background, which is different from inflationary background, from the background characterized by the classical rolling field, because there is the perturbation zeta here, so the short wavelength modes live in the background, which has already distorted by this long wavelength mode. So it's kind of inverse of separation of scales, which we are used to in the high energy physics, right? The high energy. Okay. Anyway, so so the idea is that once you can study this behavior of these modes, short wavelength modes, in the background, which already contains the long wavelength mode. And then once you know how they behave, then you can calculate this 3-point function. Okay? So for this mode, let me set the inflaton perturbations equal to 0 by choosing a gauge. Right? We remember that zeta equals to psi plus or minus plus a prime over a times minus, I guess, minus phi, where phi is the inflaton perturbation and psi is the gravitational potential. Okay? So I can choose the gauge where this phi is 0, and therefore, and that's convenient because then you will not have to worry about the change in the inflaton field itself. Rather, what you get is that your metric, the special components of the metric, the metric g mu ds squared is a squared d eta squared plus delta ij minus delta ij 1 plus psi y plus 2 psi dxi dxj. Sorry, I'm interested in the special part of the metric, so let me write down j ij equals minus a squared delta ij dxi dxj. So we have psi associated with this zeta, which is essentially the same thing. Zeta equals psi in my gauge. So what happens is that this long wavelength mode stretches out the space, right? That's the important property. And therefore, you immediately understand that the modes number 2 and 3 exit the horizon not quite at the time they did without this perturbation, psi, but somewhat later or earlier. Namely, effective scale factor, A effective, is 1 plus psi, right, times A of eta. Okay, it scales somewhat. And therefore, the condition for horizon exit is that the Hubble parameter, which is essentially constant, equals to A k over A effective. Right? That's the condition for the exit of the modes number 2 and 3, K2, 3, outside the horizon. Okay? So this means that in our expression for the perturbation spectrum of the modes K2 and K3, we have to substitute K, say 2, by K2 effective, right? Which is K2 divided by 1 plus psi, right? So we immediately write down the 2-point correlation function of this psi of K2, psi zeta of K2, zeta of K3 in the background of zeta of K1, right? Let me write this fashion, which is going to be the usual expression delta of K1 plus K2 minus plus K2 divided by 4 pi K 2 cube. And remember, we have to integrate this thing with d3k. Therefore, the fact that you make a dilatational transformation of your effective momentum doesn't play any role once I integrate. So the important thing here is that you get P zeta at K effective, right? K effective 2, say. Okay? Right, so since this P zeta depends on momentum, and we know how it depends on momentum, okay, we get immediately that this 2-point correlation function is delta K1 plus K2, 4 pi K2 cube, and then I have P zeta of K2, 1 minus d logarithm P zeta d logarithm K, and dk d logarithm K, the divergence, which is psi. Okay? I expand K effective in psi, and to the leading order in psi I get this expression here. Okay? And this thing here is nothing but ns minus 1. Okay? So the psi-dependent term in this expression here, well, there is psi-independent term, but then if you do this correlation function, it drops out. It's just the Gaussian piece. So the psi-dependent term is delta K1 plus K2 plus K3, 4 pi K2 cube minus ns minus 1 times psi, which is zeta of K1. Okay? And hence, you immediately obtain, by plugging this expression here, that this 3-point correlation function equals to this correlation function correlated with psi, with zeta. Okay? So should probably be more careful, but I should say that I have here zeta of k, say, with arbitrary k, which is low. So I mean, it's a field, and then I have to correlate it. So anyhow, what I'm going to get is that this 3-point correlation function is, first of all, that term here. Sorry, there is also P zeta of K2. So what I've got here is 1 over 4 pi K2 cube P zeta of K2 minus ns minus 1, right? And then there is a correlation between this zeta of k and this zeta of k1, which in the end gives me p zeta of k1 divided by 4 pi k1 cube, and the overall delta function k1 plus k2 plus k3, which essentially comes from this delta function because k1 is much smaller than k2 and k3. Okay? Right, so what I've got here is this is the size of this is the non-Gaussianity I have. Okay? So what people usually do in various contexts is to define the FNL, nonlinear parameters of nonlinearity, which is the 3-point function divided by the power spectra squared. So this is zeta, zeta, zeta divided by power spectra, p zeta of 4 pi, in this case k2 cube p zeta 4 pi k1 cube. Okay, this measures how non-Gaussian is your field, and we obtain very simple expression here, minus ns minus 1. Okay, this is the strength of non-Gaussianity, which is the ratio of 3-point function to the the square of 2-point functions. Okay. So this is very small. First of all, this simple calculation tells you that you are often able, or sometimes at least able, to obtain consistency conditions, if you like, no matter what precisely your inflation theory is, what your potential is. You obtain this consistency condition with which only relates the observable in principle quantities, which is model independent in a sense. I mean, NS itself and nonlinearity parameter f and L, they both depend on the shape of your potential. However, the relation itself doesn't care about this potential. I mean, this is kind of consistency condition, and there are numerous other consistency conditions you can find in literature, which is true in this case for a single field inflationary theory. We heavily use the fact that we have only inflaton that produces perturbations for you. And second, it tells you that in fact non-Gaussianity is very weak, it's very small. In the single field inflationary theory, remember this ns minus 1 with minus is a 4 of 0.04, which is very small. Remember, to measure it, the overall size of non-Gaussianity is proportional to the power spectrum squared, right? And the power spectrum itself is very small. It's on the order of 10 to minus 9. So altogether, this thing here is very small. It's very hard to imagine that it could be ever observed, but never say never. I remember we were calculating the contribution of gravitational waves to the temperature of cosmic microwave background back in 81 and 82, and when we found our final formula, we thought it will never be discussed ever. I mean, forget. It was so small, this h squared over 2 pi squared, or h squared over 1 Planck squared, seemed to be so small that we thought, forget, you will not be able ever to even, approach measuring this number, because we thought it had to do with the grand unified scale, and grand unified scale is quite substantially below the Planck scale, and therefore the expected at that time amplitude of gravitational waves was on the order of 10 to minus 10 squared. And at that time, the temperature perturbations were measured, there were bounds on temperature fluctuations of cosmic microwave background at the level of 10 to the minus 6 squared. In the amplitude 10 to the minus 3, and we thought it would be 10 to the minus 5, or 10 to the minus 6 even, and forget. Now people are approaching and put bounds which are even stronger. So never say never. For the time being, it seems that this FNL is unobservably small, but maybe in 20 years from now it will be measured. Who knows? Right, so that's non-Gaussianity, and the other models, as we will see, are easily producing much stronger non-Gaussianity, and that's interesting. Now, to finish with single field, let me comment on one more topic, which we used to hear very often, so I change gears completely, which we hear very often, which is eternal inflation and all this multiverse picture. How does it appear in the inflationary theory? Just a comment to see that it's not, just hand-waving stuff, but it's rather a very well motivated picture. The point is that if we have this inflaton potential here, phi v of phi, then classically our field slowly rolls down this potential, right, at inflationary epoch. However, there are also perturbations in this field. So this, the field not only rolls down as a classical field, but it also fluctuates as quantum field, right? And we were able to calculate its fluctuations yesterday. So the question is, who wins? Whether you have sizable probability to actually go upwards. If you go upwards, then the Hubble parameter increases rather than decreases, and therefore you have some region which inflates even stronger, right? And that's eternal inflation. Once there is a regime when there is a substantial probability that you actually, with fluctuations taken into account, the field actually has good chance to come up, to climb up the potential, then you're in business. Now the question is there such a possibility? And when, at which parameters, at which values of the field can it occur? It's very simple to study. Suppose we are talking about one Hubble time at inflation, right? So at this one Hubble time, the classical roll down, the field rolls down by this delta phi c, which is negative in this case, h minus 1 times phi c dot, right? That's the classical roll. And the fluctuation delta phi, as we discussed yesterday, is h over 2 pi, right? Square of it is the... so remember that during the one Hubble time, the range of momenta that cross the horizon out is of the order of momenta, right? Delta k is of order of k. Okay? So the horizon crossing is relation is this, is h. If your scale factor changes by a factor of 2, then the range of momenta that exits the horizon, delta k, is of the order of k, right? So if this is true, then delta phi, as we discussed, the fluctuation of delta phi squared, is integral of dk over k times p. And this term here, term here, is a 4 to 1 for our fluctuations that exit the horizon in between the two moments of time that are separated by Hubble time, right? So the square of delta phi, the additional perturbation I have on the horizon scale, or beyond the horizon scale, is p zeta, right? P phi, sorry, p delta phi. Okay? So delta phi squared is h squared over 2 pi. So the typical perturbation that you generate within the horizon, or beyond the horizon, better to say, slightly beyond the horizon, is h over 2 pi. Right? Understood? Clear. So you've got the perturbations, you've got the inflationary universe with the field phi here having long wavelength perturbations. If in the Hubble time, your within the Hubble region there appear more perturbations here, additional perturbation of the size exceeding this horizon size, whose value is h over 2 pi. Okay? So the field has good chance to travel up if delta phi is greater or of order of the delta classical, right? So perturbations here are both positive and negative, whereas classical is always negative. Classically field rolls down. But if the perturbations is bigger, quantum perturbations are bigger than the classical roll, then you have good chance to climb up. Okay, so the eternal inflation regime happens when this holds, or in other words, when h squared is greater than phi dot, modular factor of 2 pi, and phi dot is roughly modulus is roughly v prime over h, right? Remember our slow roll equations. Okay? Our slow roll equation was this: 3h phi dot equals to minus v prime. That's one of the slow roll equations. So eternal inflation regime happens when h cubed is greater than v prime, and since my h is related to the value of the potential by the Friedmann equation, this gives me the relation v 3/2 over m Planck cube v prime must be greater than 1. Okay? Since my Hubble parameter squared is v divided by the Planck mass squared. Okay? So modular factors of pi and numbers, this is the condition for the eternal inflation regime. Okay? Can this be the case? Well, sure, it can. You can easily convince yourself that there is a range of values of phi for which the energy density is still sub-Planckian, but this condition is satisfied. For example, consider potential V, which is m squared over 2 phi squared. Okay? then this condition here will become m cube phi cube divided by m Planck cube m squared phi, right? I just plug this potential in here, which gives me m phi squared over m Planck cube. Must be greater than 1. Okay? Obviously, since my m is much less than m Planck, and for successful generation of density perturbations, we need m over m Planck of 4 × 10⁻⁶. Why is it? That's because we know what the amplitude of perturbations generated is, and as we discussed yesterday, it is related to the coupling constant. Here, coupling constant is m. Coupling constant must be small in Planck units, and if you do your calculation of the amplitude of density perturbations, then you get this number. So this inequality is stronger than the inequality for successful inflation. Inequality for inflation is that phi must be greater than the Planck mass, right? The phi must be super Planckian, and then the universe inflates. Here it's stronger, right? Because phi must be greater, phi squared must be greater than m Planck cube over m. But still, this is the subplanckian regime, because the energy density V is m squared phi squared, right? So it's m times m Planck cube, which is much less than the Planck scale, m Planck to the 4th, right? So you need to be high up here. So the inflation ends when the phi is somewhere near the Planck scale. So this up here, it's inflation regime, and eternal inflation is kind of geometric in between the Planck, the quantum gravity regime, when the potential is m Planck to the 4th, and here is the end of the eternal inflation stage. Okay, so if you are somewhere here, you are in the eternal regime. So if your field starts off at near the quantum gravity regime, when the energy density is somewhat below the m Planck to the 4th, if you start off somewhere here, then you are inevitably in the regime of eternal inflation, right? So it's quite natural that you have the eternally inflating picture, in which in some of the parts of the universe you still inflate, and in other parts inflation already ended, and we turn out to be in the latter situation. Okay. Also, it's nice that you don't inflate eternally near the end of inflation. That's nice because otherwise all our perturbative calculations would not be correct, right? We'll have to worry about, inflation continuing and continuing as we approach its end. That's not true. Here we have the perturbative regime where quantum fluctuations generated during inflation are small, so that our overall picture of classical field rolling down and small fluctuations about this classical field is correct. So this consideration tells us that we didn't do anything wrong. We did correct calculation when we calculated in linear perturbation theory the density perturbations that are generated, because here the horizon crossing of interesting modes occurs when we are near the end of inflation, somewhere here, and we are far away from eternal inflation regime. So we are safely in the linear approximation. Any questions so far? No questions, good. All right, so let me change the gears again and consider a completely different mechanism of generating the density perturbations in the universe, which goes under the name. There are many. It's not the only one. There are many mechanisms which employ additional fields beyond the inflaton. And I just have chosen one at random, since I can illustrate various properties which are absent in the single field inflation. So curvaton mechanism. That has to do with extra field, right? Single field inflation is over, essentially. So we need extra field. Let's call it Q, curvaton. And let's assume that at inflationary epoch it is a spectator. So that its potential energy is small compared to the inflaton potential. So inflation proceeds, as we discussed, with the inflaton field phi playing the role, whereas this guy Q is a spectator. And I'm going to illustrate things by choosing the simplest potential for this curvaton, which is mq squared over 2q squared. Although you can study more general potentials. In general, this curvaton is not going to stay at zero of its potential, at minimum of its potential. If mq is small, then now it's a curvaton potential, V of Q. Then if it starts off somewhere, it will stay there at inflationary epoch. Why? Because the equation for this Q in cosmic time is Q dot dot plus 3H Q dot plus M squared Q equals 0 if it's a homogeneous field. So if you put it somewhere up here, it will stay there provided that H is much greater than MQ. So for small masses, your Q is frozen out at a certain value, which is the initial condition for its evolution later on. And we don't know what it is. It can be any. So that's one property. So your extra field, your spectator field, stays at some non-zero value generically. Second is that it also develops perturbations, delta Q, whose amplitude is h over 2 pi, right? So this is a massless, essentially, effectively massless scalar field. I neglect this mass compared to the Hubble parameter. So it's negligible in the equation of motion for modes of this field. And therefore, everything goes through as we discussed yesterday when we studied the evolution of perturbations of quantum massless scalar field in the inflationary background. Okay. More precisely, the power spectrum of this Q, delta Q, is h squared over 2 pi squared. This is the Gaussian random field with this power spectrum for the time being. Okay? So there is fluctuations of this field here. And these are fluctuations in energy density as well, right? Since my potential is non-vanishing, it's also fluctuations in energy density. But clearly, initially, these are entropy fluctuations, right? These are fluctuations in energy density, but not in the gravitational potentials, because this is not the dominating matter at inflationary epoch. The dominating matter at inflationary epoch is inflaton itself. Okay, however, these are easily reprocessed into adiabatic perturbations at later stage. So what I'm going to assume is that perturbations generated due to inflaton itself are negligible. The parameters in the inflaton potential are such that the amplitude of perturbations generated by a mechanism we discussed yesterday is small. It's so small that they are negligible as compared to observed density perturbations. Okay? For example, in the quadratic inflaton potential, the inflaton mass is much, much smaller than 10 to minus 6. Then you get negligible contribution from the inflaton to density perturbations. Now, what remains are perturbations in this field, okay, and they can be reprocessed into the density perturbations. How this can happen? Well, at some point after inflation, when this condition becomes violated, this field Q will roll down, right? It will roll down, it will oscillate, and oscillating field, it can be viewed as a collection of static quanta with zero spatial momentum, right? It's a condensate of these quanta. And if this field Q interacts with the standard model particles, it will decay into standard model particles and reheat the universe. And transmit its energy into the energy density of conventional particles, just like the inflaton does. Okay? So I will be a little bit sloppy, and therefore the numerical factors will not be completely correct. But to give you an idea, at this moment of time, my energy density in this Q field is V of Q. Q is sitting in here before it starts to oscillate. So it's m squared over 2. So let me call it QC, classical field, which is going to start oscillating. It's homogeneous part. But also, for modes which are outside the horizon at that time, and we are interested in those modes, which are outside the horizon at early epoch, we are talking about pretty early epoch when the, if this MQ is not particularly small, then the Hubble parameter was quite large. This is early cosmological epoch, so we are interested in modes which are superhorizon at this epoch. For them, in a given horizon, or there is perturbation also, delta Q. So the field starts oscillating from squared, from different values of Q in different places in the universe, and therefore the energy density in this field is different. Right, so I have energy density transmitted to radiation from inflaton, and I have extra energy density sitting in this potential here. So my total energy density, rho total, will be the energy density in the radiation, which descends from the energy of the inflaton, plus energy density V of Q. sitting in this field Q. And since this V is inhomogeneous, energy density sitting in this Q is inhomogeneous, the total energy density will be inhomogeneous. And I assumed that inflaton perturbations are negligible, then this rho radiation is constant over space. There are no perturbations in here. In radiation, there are perturbations in this Keroton field. Okay? Right, so what is the delta? Delta is delta rho total over rho total. Right? This is delta V over V times the ratio of V to rho radiation plus V. Okay. And let me call this RQ then my delta, the perturbation in the energy density, is basically RQ, which is the ratio of energy density of the curvaton to the total energy density times delta V over V. Okay? So I do generate perturbations with flat power spectrum, nearly flat power spectrum, right? If I'm doing linear part, then this term will be like RQ, then there will be 2 delta Q over QC. Okay? This will be a linear part, which has nearly flat power spectrum, again, since my Hubble parameter at inflation doesn't change much in time, and therefore, I mean, this is the same story as for gravitons. It's slightly red, which is consistent with what we have. So we have slightly red power spectrum with tilt equal to the tilt of gravitational waves, which is a different story, completely different from what we have in the case of single field inflation. That's one difference. The scalar spectral index equals to the graviton spectral index, tensor spectral index. They both come from the same H, from the same Hubble parameter. But besides that, you also have another thing. Another thing is that this delta V, the difference between V and the classical value, involves as well another term, which is delta Q squared, delta Q times delta Q over QC squared. Right? Which is a non-Gaussian feature. Right? Your perturbation is no longer linear, so delta Q is Gaussian, okay? But its product on itself is not. This is, so what we get here is that this is true in the coordinate space, right? So in the coordinate space, my delta of x is the following thing. It's a linear part, which is, or Gaussian part, delta Gaussian of x, and this is this term here. I call this delta Gaussian of x, And the rest is expressed in terms of this delta Gaussian plus 1 over 4 delta Gaussian of x squared. Okay? So even though my original perturbations in the curvature field are Gaussian, perturbations in energy density and therefore adiabatic perturbations, I'll identify this with adiabatic perturbations now, because these are the only perturbations that, after the decay of this curvaton, what remains is the hot plasma. So there is a single component fluid. Perturbations in single component fluid are by definition adiabatic perturbations. Therefore, my adiabatic perturbations are basically a linear combination of Gaussian field and square of the Gaussian field, right? And depending on, this is RQ, for RQ. And depending on this RQ here, you find that these perturbations can be strong. The point is that if the contribution to the energy density, RQ, this is it, if it's small, at the moment when the oscillations start and the curvaton decays into conventional particles, if the energy density compared to radiation is small, this means that to get the sizable perturbations in energy density, you need large perturbations in delta Q, right? Because just because the contribution of this curvaton to the total energy density is small, perturbations in the curvaton energy density give small contribution to the relative perturbation in the total energy density. Therefore, this guy should be large, and therefore this non-Gaussian piece should be large. That's why there is enhancement by 1 over RQ. So, in principle, non-Gaussianity can be large. And there was some, hope that the study of non-Gaussianity by Planck will reveal non-Gaussianity of this sort. This is called local type of non-Gaussianity. Local in the sense that the non-Gaussian part is proportional to the square of Gaussian part in the coordinate space. Therefore, it's called local. Okay? So, the standard definition is that zeta, I'm skipping one part, which is the translation of this energy density perturbations to zeta, but it's a technicality. So zeta here, in this case, the standard definition is that it's Gaussian zeta minus 3 over 5 zeta Gaussian squared times F and L. This is another measure of non-Gaussianity, local. And the present bound on F and L local coming from Planck, which is actually quite strong, amazingly strong. It's 2.7 plus or minus 5.8. That's the Planck value, which is quite strong, right? So with the curvaton mechanism, you expect this FNL to be possibly quite a bit larger than 1, and at least roughly for the 1. Once you have a curvaton mechanism, you expect this FNL to be for a 1. And we are approaching very closely to that. Okay? So if it would be possible to get 1 order of magnitude down from here, and remember, Planck got down by an order of magnitude compared to W map in this parameter here. So the point is that if one will be able to go down by another order of magnitude, the curvaton mechanism will be ruled out. And many others which produce sizable non-Gaussianity. So we are starting probing inflationary scenarios with negative results yet, but we are starting probing quite natural, in fact, inflationary scenarios. This is quite natural mechanism of generating the density perturbations, which employs just another scalar field. Why not? Any questions so far? Okay. Let me also use this example to talk about isocurvature modes. Okay. Same example. Now you can ask, if you have this extra field, do you generate isocurvature modes as well? Well, you have to be a little more contrived. Here, I assume that my meta radiation, I called it, actually is in complete thermal equilibrium, right? So dark matter for particles, for example, are still in thermal equilibrium with conventional particles. And baryon symmetry was not yet generated. So I was assuming that this is a single component fluid. Dark matter particles are in chemical and complete thermal equilibrium with the rest of the plasma in particular. But this need not be the case. So if we want to generate the isocurvature perturbations, then we have to assume, of course, that after this curvaton, at the moment the curvaton decays, there is no thermal equilibrium between dark matter particles. I'm going to talk about the dark matter isocurvature, dark matter entropy perturbations. So I have to assume that dark matter is not in thermal equilibrium with conventional matter, because otherwise this is one and the same fluid. Dark matter and conventional matter is one and the same fluid, and therefore there is only one type of perturbations, which is adiabatic perturbations. So we want to make a difference between adiabatic and entropy perturbations. We want to have entropy perturbations at all, then we will need that dark matter has already decoupled. So dark matter decoupled. Decoupled means that there is no equilibrium between the dark matter is free. Consists of free particles which do not they can scatter off our conventional particles, but they cannot change their number. So number of dark matter particles is doesn't change due to their, say, annihilation or creation. Okay? In this sense, there is no decoupled in chemical sense. The number density doesn't change due to interactions with conventional particles. Then these Q particles, the curvaton particles or curvaton oscillations, can decay into dark matter and conventional matter radiation. And these will not talk to each other. Right? That's a scenario. Now, radiation will, of course, thermalize. That's our conventional stuff, quarks and leptons, photons, etc. If this happens when the temperature in the universe is negligible, in other words, if this happens when this Q dominates completely, then you do not generate any entropy perturbations, because the universe is the same everywhere, right? Even though you have perturbations in Q, if Q is the only component before it decays, it will produce equal ratio of dark matter particles to radiation in its decay. And this means that entropy per dark matter particle will be the same everywhere, right? So remember, our measure of whether you have entropy perturbations or not is whether the dark matter number density over entropy density varies in space or not, right? If it varies in space, then it means that I have entropy perturbation. If this Q is the only source of energy, then this ratio will stay constant, will be constant in space, even though the decays will happen somewhat earlier, somewhat later in the universe because of perturbations of this Q, and energy density in different places in the universe will be slightly different, but this ratio will be the same. It will be determined by the ratio of dark matter to radiation in decays of these Q particles. Okay? However, if there is some entropy initially, if these decays occur when there is hot plasma around and there is some entropy in this hot plasma, then obviously you're going to get entropy perturbations, because in different places in the universe, this ratio generated, the number density and entropy density generated will be the same, but it will be different in different, but since energy density in Q is different in different places in the universe, there will be different number of particles and radiation produced in different places in the universe, but on top of that you have also the homogeneous part in the entropy. And therefore you will get non-vanishing or especially varying ratio. So what we are going to get from these decays, the number of dark matter particles divided by the entropy produced in decays of the Q particles is constant throughout the space, but the upper part and lower, the numerator and denominator are different in different places in space. Okay? So this ratio varies in space, okay? Because this ratio is now m dark matter over S produced in decays times S produced in decays divided by S produced in decays plus S existing already. Okay, this thing here is constant, but this thing here is not. It varies in space. Okay, and this is a small effect. Let me assume that S initial is small. Otherwise, this will be a large effect, right? This entropy perturbation will be large. I don't want it to be large. I want it to be small. So I want this Si to be small, and then this will be varying in space the amplitude of its variation will be small. So what I get here is n dark matter over S. This is the first term. Then S initial to S total, you have the suppression factor. From here with possibly minus sign. And delta S the perturbation of the entropy which is generated during the decays, this depends on X now, right? So this S decays depends on X, right? And here I can safely set S as the total entropy density, homogeneous part, and this is inhomogeneous part, right? Clear. Now, this is the entropy perturbation, and if the adiabatic perturbation dominates, then this is proportional to zeta, right? Because it's delta t over t, 3 times delta t over t, the variation of temperature in space, and effectively it's 3 zeta. Okay, remember our calculation for adiabatic mode, that temperature fluctuations in our conformal Newtonian gauge are related in this fashion to zeta. So all in all, I get that, I should write down the specially varying part, I get that this S we introduced, which is delta n dark matter over S to n dark matter over S, the relative perturbation in dark matter to entropy ratio, which characterizes the entropy, dark matter entropy mode, okay, is this small factor, the existing entropy before the decays of Q particles to the total entropy, which is generated in the end, times 3 zeta. If I am not mistaken, it's with minus sign, but for me. So you do generate, indeed, I think the sign must be positive here. How come is it positive? I think it's positive here, but oh, yes, it is positive. Right. You write that S decay of X is S decay homogeneous part plus delta S decay, and then you expand in this delta S decay. Right. Then it will be negative sign coming. The sign is important here. Negative sign coming from here when I put it into the numerator, and another negative sign coming from the. So I write this thing here as 1 minus Si over S decay. Right. This is homogeneous part. This is not, and then this is going to be. Again, delta S in denominator, so the sign will be flipped again. So the sign is positive. Right. So the sign is positive. What's interesting here? Interesting here is that this measure, this field of the Gaussian field of isocurvature perturbations is proportional with positive sign to the adiabatic perturbation. Weird, right? You won't expect that the entropy perturbations can be at all related in space to adiabatic perturbations, but they are. In this particular case, there is a complete alignment. Whenever you have zeta positive in some part of the space, at the same part, the entropy perturbation is also positive. So there is complete alignment of entropy or correlation, positive correlation of entropy perturbation with adiabatic perturbation. That motivates the study. So people who are doing analysis of, say, Planck data nowadays, they do look into this possibility. This is totally correlated case when entropy perturbations are totally correlated with adiabatic perturbation. You can design more contrived models where there is a total anti-correlation between the two. And sometimes you have uncorrelated cases. The axion case which I wanted to talk about is uncorrelated. The entropy perturbations in the axion dark matter are uncorrelated with adiabatic perturbations. Here, with curvaton mechanism, you see it's easy to generate entropy perturbations which are correlated with adiabatic perturbations. Can we do anti-correlated? Yeah, we can. Which is a little more contrived case. Here it's relatively natural, but if you want to explore various possibilities, you should allow yourself to be relatively contrived. The anti-correlated case, example of anti-correlated case, is again with this curvaton scenario, but then you assume that, well, how do you do anti-correlation? I mean, easy. If you've got correlated perturbation by assuming that there was some entropy before the decays, if you want anti-correlation, you want the numerator to exist before the decays of these curvaton particles, right? So if you have some addition to this S and that led to total correlation, then if you have some addition to the numerator before the decay, then you will obviously have anti-correlated entropy perturbation. And that's indeed the case. You can say that suppose I have dark matter particles now existing before curvaton decay. So my inflaton, for example, can decay into, radiation and dark matter particles. So there are dark matter particles beforehand all the time. Radiation redshifts away like 1 over a to the 4th. So by the time when this curvaton decays, it may disappear, whereas the dark matter particles may, their energy density decreases slower, like 1 over a cube, and therefore they can remain. That's the scenario. Okay? So suppose that the number of dark matter particles after the decay is the number of them produced in decays, dark matter particles, and number of dark matter particles which existed before the decays. Okay? Then what you're going to get is that this ratio here And entropy you generate only due to the decays of the S is due to the decays of the Keroton particles. Okay? Then what you're going to get here is the ratio of n, the number of density of dark matter produced in decays, into entropy produced in decays, which is constant throughout space, right? Plus extra term, which is Ni over S decay. And this guy depends on X, and I does not. Okay, then I again write that S in decays is S average of the universe plus delta S of X. And so it's just S average in the universe produced in decays, and 1 plus 3 zeta, as we agreed. So I plug this in here and get that my inhomogeneous part of this expression here is minus Ni over n decays, and dark matter produced in decays over entropy, average entropy produced in decays, times 3 zeta. Okay. So my S, again, which is the ratio of fluctuation to the average value of n over S, is going to be minus Ni over n dark matter total. And I'm assuming that this is a small number, so the total dark matter is mainly due to the decay, times 3 zeta. And as promised, I got anti-correlation between the entropy mode and adiabatic mode, right? So with all in all, with Keroton, you can get sizable non-Gaussianity. The easiest thing is to get non-Gaussianity of the local type, like here. You can get entropy modes, which can be either anti-correlated or correlated with the adiabatic mode. Correlation in space, which means that if you calculate the two-point functions, for example, there will be a two-point function, the cross correlation to two-point function of this sort. Since my entropy mode is proportional to the adiabatic mode, there will be a cross correlation of this sort. Okay? Which offhand sounds very strange. If you don't have this idea of the Keroton, this would be very contrived. You will not think that there will be any relationship between the two, between the adiabatic and entropy mode. But these examples tell you that it's quite possible that you can have this non-zero correlator. And if there is such a correlation, then of course it's easier to search for entropy mode, because its effect is linear in its amplitude, right? Therefore, the limits on the entropy mode, which is either correlated or anti-correlated with the adiabatic mode, are quite a bit stronger than for uncorrelated axion-like entropy mode. Yeah. Well, you have to say, okay, I have as an initial condition for my perturbations, I have a adiabatic mode, okay, with all its properties, and I also have this S mode, okay, the entropy mode, which is a different initial condition. Now my theory is linear, therefore I can follow the evolution of the adiabatic mode and this mode independently. These are just two different initial conditions. The total perturbation is the sum of the two. Okay? And then I obtain in the end the values of various quantities, say Sachs-Wolf, the things that enter Sachs-Wolf effect, as the linear combination of these two, right? And then you do all this CMB stuff, and in the end you end up with measuring this kind of, what enters in the end is the 2-point correlation function of the total perturbation, okay? Which is basically the sum of, say, the Sachs-Wolf term, delta gamma 1/4 plus phi, is a sum of two things, zeta plus the same thing with S, okay? And my CLM, the CL, the temperature anisotropy coefficients are expressed in terms of 2-point correlation functions of these guys, of the complete perturbation, okay? Right? Now, the 2-point correlation function depends on whether you get vanishing or non-vanishing correlation function of this sort. So your total result will involve, the total result for CL will involve this correlation function. Okay? Did I answer? I mean, that's the idea. The idea is that you actually measure the sum of entropy and adiabatic and entropy mode, the complete density perturbation, and this sum involves both adiabatic and entropy mode, and its 2-point correlation function involves the correlation function of this sort. Okay? And now the effect of this guy on the density perturbation is different from the effect of that one. The density perturbation generated, as I showed you the pictures, density perturbations generated when the initial conditions are entropy is different from those with adiabatic initial conditions, and therefore you can disentangle them. All right. I think I don't have time to go further, so I better stop here. Yeah, I think discussing reheating will be more than 5 minutes, so I'll probably stop here.